Today we're going to be talking about essential techniques with special trig limits. The learning target is I can use algebraic skills to calculate special trig limits. So from our last lecture, we graphically saw these three special trig limits. So the limit as x approaches 0 of sine x over x was equal to 1. We saw that visually with the graph. 2, the limit as x approaches 0 of x over sine x was also equal to 1. And 3, the limit as x approaches 0 of 1 minus cosine x all over x was equal to 0. Again, we just graph these. You could use a graphing calculator and or Desmos to see these limits. But we're going to push ourselves to further extend our special trig limits into these. So the limit as x approaches 0 of sine of blank all over blank is equal to 1. As long as these two blanks are the same, you could say that the limit is equal to 1 as x is approaching 0. So again, now this is for my b right here. It's going to be blank all over sine of blank. The limit as x approaches 0 is still going to equal to 1 as long as these blanks are equal and the same. So again, let's look at our c. The same applies. So what does that look like? We're going to take a look at some examples. All right, let's take a look. So take a look at example 1 here. It says sine of 3x all over 3x. What is the limit as x is approaching 0? Our blank, see if we're looking at part A, our blank right here, blank blank is 3x and 3x. Because these two are the same, we can therefore use this rule that the limit is equal to 1. All right, let's try another example. Example 2. So because this is like our x over sine x, I'm going to be looking right here at my b. Because this is equivalent to this, because negative 5x is equivalent to negative 5x, we can use this theorem right here. The limit as x approaches 0, therefore, of this whole quantity is just going to give us 1. All right, let's take a look at this example 3. Again, now we're looking at c right here because this is the 1 minus cosine x all over x rule. So blank is equivalent to blank. Here our blank is pi x all over pi x. So because these two are the same numerical values, we can therefore use this theorem and say that this right here, the limit as x approaches 0, is equal to 0. Example 1, 2, and 3 are basic uses of how to use the theorem. There are other examples and other problems that you will have to do that require algebraic manipulation to get your answer. All right, so how are we going to be using algebra to apply the special trig limits? So let's take a look at example 4 right here. So first off, this looks an awful lot like sine x over x, so we're taking a look at a right here. That is my first special trig limit. The issue with this problem right here is that this is equal to 3x, yet this does not equal to 3x. Remember, in order for this theorem to work, this square has to equal to this square. This blank must equal this. So I need to try to get 3x down here. Not down here, but I gotta try to force this denominator to have a 3x at the bottom there. How will I do that? So, because this is a fraction, no matter what I do to my denominator, I must do to my numerator. So, why don't we just multiply the top and bottom of this by 3? We have to do the top and bottom because, like I just mentioned, if you do something to the bottom of a fraction, you must do it to the top, like so, because that's like multiplying by 1 in that case. So that doesn't change your fraction. So when I multiply top and bottom by 3, I'm just going to multiply across here to combine these. Great. So now if we just look at this chunk right here, sine 3x over 3x, I know that the limit of that chunk as x is approaching 0 is equivalent to 1 using this theorem. So therefore, I'm just going to separate, or I'm going to bring out that 3 so I can isolate the chunk that is equal to 1. Because this is like 3 over 1 times this, so I can pull out the 3 here. All right, so now let's just take the limit of every single component here. So the limit as x approaches 0 of 3, and the limit as x approaches 0 of my sine 3x all over 3x. All right, so I know that the limit as x approaches 0 of 3 is just going to be, okay, that's just repeated, is just going to be 3. This right here is just 3 because the limit of a constant is always usually just the constant. There's nothing for you to plug into, so it's just 3. Then right here, I am using part A. Sine of 3x over 3x, the limit as x approaches 0 is equivalent to 1. So that's why I wrote times 1 right here. Once I take the limit, you notice that my limits disappear. So it's just going to be 3 times 1. That's equal to 3. That's your answer for example 4. So you notice how we did all this algebra to figure that out. You might notice a pattern with some of these, but it's not always useful to rely on a pattern when you come up with a new example that requires your algebraic manipulation. So let's keep going with these. Example 5. So this one looks like part A again. Yeah, sine of 1/2 x all over x. So again, we got to make sure this denominator right here, this x, looks like 1/2 x, because in order for us to use this theorem right here, blank has to be equivalent to this blank. So let's repeat what we just did before. I'm gonna multiply the top and bottom by 1/2 so that I can get a 1/2 right here in my denominator. But because I multiply the bottom by 1/2, I must do the same to the top. So there we go. I color coded this 1/2 into blue so that you can see that this chunk right here is going to be equal to 1. And then I'll be pulling out this 1/2 in the front. There we go. Then we're going to break these up into 2 separate limits, because when you have the limit of a multiplication, you can definitely do that. You can separate these into 2 different limits. Alright, so the limit of 1/2 gets pulled out. Then we got the sine, the limit as x approaches 0 of 1/2 x all over 1/2 x. This, by using this rule right here, is equivalent to 1. And then the limit as x approaches 0 of 1/2 is just going to give us 1/2. So 1/2 times 1 is 1/2. Alright, that's example 5. Let's keep going with this. So for some reason, there's a tiny example 6 right here. Anyway, let's just go ahead and begin. So I'm pretty sure I want to have my rules up here. That's what's not showing, but basically we know that the rule is that this blank must equal this blank if you have the handout in front of you. So in order for me to get a 6 down here, I should make sure that I multiply top and bottom by 6. Trying to figure out how to, oh well, we'll take care of that later. So anyways, I multiply top and bottom by 6, so I get it to look like my rule, my theorem, which should show up on your paper. I multiply by 6 to get this. So top and bottom by 6. You got to remember, I put a parenthesis around here because it's 6 times this whole quantity up here. Alright, so now this chunk right here looks like my 1 minus cosine blank, or box, all over blank. So I know that this right here, for sure, I know the limit is going to be 0, because as x approaches 0, that quantity was equal to 0 according to the theorem. So I pull out my 6 out in the front like usual. I separate it into 2 separate limits. I know for sure that this is 0, and I know that the limit as x approaches 0 of 6 is just 6. It's just going to be 6 times 0. And anything times 0 is just 0. So basically from here, we could have already seen that fact, or already from here into that step. So you don't have to go into further steps if you can already see that limit. Awesome. All right, here is example 7. So this one's very interesting. Not only are we missing the fact that this denominator does not look like this part right here, we're not just missing the 3, but we even have a 5 here. So we think about how we're going to deal with that. Well, with some algebra, that's what we're going to do. So here's the step. I'm going to start my step as usual because I know that I want a 3 in my denominator. I don't have a 3 there, I have a 5, but I know I need a 3 there. So what we're going to do is we're going to continue and still multiply the top and bottom by 3. Great, let's go ahead and do that. Let's combine these into a fraction. Alright, so I got 3 times sine of 3x all over 3 times 5x. Let's just scooch this 5 over here. You notice how I did that? You could do that in math because a times b is equal to b times a. So you could definitely switch multiplication like that. And I did that so that you can see that once I do that, I get my sine 3x over 3x, which is what I want. The limit of, as x approaches 0, of sine of blank all over blank was equal to 1, according to your theorem that you have at the top of your page. So that's why I did. That's my algebraic technique right there. That's the plan of what we're doing. So great. Let's go ahead and take care of. We're going to pull out the 3, and I'm going to pull out the 5 out in front of my fraction like so. See how I just pulled that out? You can do that because you can always reverse it, because we know that multiplying fractions, you just multiply across. So this makes sense that you can move backwards. So I pulled out the 3/5. Great, I have my limit of sine of blank all over blank so that I can apply the theorem. I go ahead and take the limit of both sides. I don't know why this is color coded, but I know that the limit as x approaches 0 um, of this expression is equal to 1, and I know that the limit as x approaches 0 of 3/5 is just 3/5 because that's a constant. You get 3/5 times 1, which is just 3/5. So that is your limit for this problem. This will be for later. That is the end of our notes. Once you're done, please raise your hand and you'll get the task. Thank you, and let's do this again.